popular problem type for you, and I'm just going to write down the general form of this problem type. You can generate your own problems from this, but this all hinges on just definition of logarithms, and then you end up with this form at the very or near the very end of the problem, where you can see this is in the form a plus b, and then this is a minus b over here. All right. And so the problem is actually designed to work out very nicely, but you can gen as many problems as there are natural numbers. Okay, so you see a lot of these problems flying around. Now, now let's get back up to the problem. It's tempting to want to use this rule right here. This is the log of a quotient. This is well known that the log of a quotient is the difference of the logs. But notice this isn't in the very same form. This is the quotient of the log. So it's a linguistic distinction too. This is the log of the quotients, and this is the quotient of the log. So you can't apply this as much as you want to. So what we do is we resort to the definition of logarithm. Any logarithmic statement has a corresponding exponential statement. Okay, and really it's just because base 10 here and log base 10 are inverse functions. You can think of raising this entire expression to the 10th power, and you end up with this statement right here. And the base of the logarithm means nothing for the result of the problem. Okay, so anyway, you get these two statements. You get the whole thing is equal to x is equivalent to 10 to the x is equal to the input, and similarly right here. So very straightforward. This is literally a definition. These are two definitional statements of logarithms. Okay, now if you multiply them together and use properties of exponents right here, notice this is a plus b, a minus b, as I said earlier, and this is in the form a squared minus b squared, and you can see that. You get m squared, and then when you square this object, the radical goes away, and you have minus m squared minus 1, which is minus m squared plus 1, just leaving 1, okay? Now, a nice thing happens right here that leads to an immense simplification. Notice that the only way you can have an exponential equal to 1 is if this the exponent itself, the exponent expression piece, is equal to 0. That is, b raised to the 0 is equal to 1, right? All right, now that implies in this context we get 10 to the x plus y is equal to 1, that x plus y must equal to 0. All right. And of course, that tells us that x is equal to negative y. Okay, now it's going down. Now let's take a look at our original problem. Remember, the original problem is equal to x over y, and so this would be equal to, if x is equal to minus y, we can just write this as minus y over y, right? It's equal to negative 1 provided y is not equal to 0. Okay, so that is our solution in the general case. Now let's just take a look at a concrete case right here. Notice you would have the form right here since 15 squared is equal to 225. Let me write that down. 15 squared. And this is just a special case that I made up. And literally, you can gen as many of these problems as you want. 15 squared is equal, and it probably works for all real numbers, all rational numbers, you know. Maybe even complex numbers for complex logarithms, you know. But this is equal to 225, 15 squared. And again, I just arbitrarily chose these constants here. And of course, 15 squared is 225 minus 1 is the 224 you see right here. So we know, without going through all the computations again, that's equal to negative 1. And again, this is the kind of problem I've told you that I've seen quite a bit of, you know, where people just make up these problems all over the place and go through all the computations. But really, anytime you have this form, it's always going to be equal to negative 1. So hope you enjoyed.